I'm happy to introduce the third talk of this session. Francesco Cattafi from University of Leuven will talk about decoupling Cartan connections and coupling G structures, a Cartan bundle story.
Yes, so thank you very much, Anastasia and Nikita, for organizing this wonderful conference and invited me. So indeed, today I will tell you this story about this object, this Cartan bundle. This is based on a preprint which I have in the archive and some ongoing joint work with Luca Cornero, who is at the University of Utrecht. So what I'm going to talk about in this first part will be mainly to explain this first line. So what are these Cartan connection and G structures? Mostly a reminder for people that don't know it, for people that know it, and explanation for those that don't know. And we will see that this Cartan bundle are a new notion that sort of interpolate between these two concepts. At the very end, then I will actually establish some correspondence between Cartan bundles and a class of Lie groupoids. So Lie groupoids will enter into the picture only at the very end, so you don't have to be scared if you don't like it for the first part. And then in the parallel session, I will actually say more about this about this correspondence, about this class of Lie groupoids that gave rise to Cartan bundles. So I put here the word pathfinder just to give a spoiler, and further topics for those that will be interested then. So let's start with the Cartan connections. So what are those? Those are a kind of connection principal bundle. And I would say that they are a well-established object, but usually people, when think of Cartan connection or think of a connection principal bundle, have in mind this other object, an Ehresmann connection. So let me remind you that an Ehresmann connection, a principal bundle, consists precisely of a one form with its values in the Lie algebra of H of the structural group and satisfies certain properties. And which are these properties? You need to ask that the form pointwise is a surjective linear map. You want the form to be H equivariant with respect to the H action on P and a joint action of H on its Lie algebra. And you want also that for any element of Lie algebra, if you consider the fundamental vector field, this V dagger, which is defined using the infinitesimal action, if you apply theta to that vector field, you get back the element of the Lie algebra. So this is one possible definition of Ehresmann connection. There are other equivalent ones. But I wanted to use it as a starting point to say that a Cartan connection is something that looks like an Ehresmann connection, but there's a key difference, which it takes values in a bigger Lie algebra, some Lie algebra G, which contains H. So in order to give this definition, indeed, one needs first to choose some data. These data are called a model geometry. Now, the word model at the moment may not be clear yet to you. Hopefully, it will be in the next couple of slides. For the moment, just think that we need to make some choice. These choices are the choice of a Lie algebra, a Lie subalgebra with an integration H, and we also need a representation of H on G. Now, if we have this data and we have our principal H bundle, by definition, we can talk about Cartan connections modeled on GH. And what are they? They are, again, a one form on P with values this time in G, in the bigger Lie algebra. And is such that at any point, it is not only a surjective map, it is actually a linear isomorphism. So this is the fundamental difference with Ehresmann connection, that in the first case, you know that if you take here the kernel of the form, this defines actually a distribution, which is a horizontal distribution. This would be an equivalent way to talk about Ehresmann connection. But for Cartan connection, this is not the case, because the kernel of this form is zero, since it is a linear isomorphism. So these are quite different kind of object. The other properties 2 and 3 are instead exactly as above, because you can still make sense of equivariance, because you have the action of H on P, and you use this representation H on G, and also the third property makes perfect sense. So this is what is a Cartan connection, and then a Cartan geometry is just the set of all these three data together. So the principal bundle, the model geometry, and this differential form, this Cartan connection. Now, this definition seems a bit abstract because it doesn't tell you much. I'm just giving you a form and some conditions. So I would like to try to give you some intuition on those. Let me only just first tell that this Cartan geometry is a quite strict, have some quite strict requirement because it follows actually from those property. First of all, that you cannot choose randomly the representation that you want at the beginning, because it must actually extend the adjoint action of H on H. And also, if you have a Cartan geometry on M, then the tangent bundle of M actually must be diffeomorphic to this other vector bundle. This is the adjoint vector bundle, adjoint to P and G over H, where G over H is also actually, it follows that it is a representation of the group H. precisely because of this property. And in turn, this implies that there is a dimensional constraint on M. So M actually must have this dimension as the difference between the dimension of G and the dimension of H. And other properties, which now they're not really relevant for the purpose of this talk. But as I say, I wanted to say how this Cartan geometry were born, why they are interesting. And to do that, I need one more definition, but this should be quite easy. It is that of curvature of a Cartan connection. So the curvature is defined in this way, with this formula that hopefully looks quite familiar for most of you, which is indeed just a two-form with values in G. So note that here, this bracket here, I'm really using the fact that G is a Lie algebra, so I can take brackets there, because for the actual definition, G was only needed to be a vector space in principle. And now why I want this curve to define this curvature? Because the informal way to talk about Cartan connection is saying that they are the curved version of Maurer Cartan forms on Lie groups. So what does it mean, this sentence? It means the following, that if you consider a Lie group G and a Lie subgroup H, then of course you can see G as a principal H bundle over this quotient manifold. And then you can consider the Cartan form, the Maurer Cartan form on G. So this is a one form on G with values on the Lie algebra G. And this form actually, because of how it is defined, satisfies all the property of a Cartan connection in a quite trivial way, because indeed for how it is defined, it must be pointwise surjective, it is invariant, and so on. And moreover, it is flat, meaning that, this formula here become then the standard Maurer-Cartan equation, which is indeed satisfied by the Maurer-Cartan form. So it means that this Maurer-Cartan form has zero connection. And so, just rephrasing what I just said, you can say that any Klein geometry, and by Klein geometry I just mean this couple of a group and a Lie subgroup, define a canonical flat Cartan geometry, which is really given by this principal bundle and this Maurer-Cartan form as a Cartan connection. On the other hand, if you take any Cartan geometry which is flat, so which has this curvature that we defined before, which vanishes, this locally will look like a Klein geometry. So now here, hopefully, it is clear why we talked about model geometry before. So you should really think of Klein geometries, Maurer-Cartan forms are sort of local model of Cartan geometries. And it's not only that you should think about it, this is really how historically they were thought of, because they were inspired by a similar picture that happened for Romanian Manifold. So in the case of Romanian Manifold, you know that, I mean, their local model is actually Euclidean geometry. So what we call now the Romanian Manifold from the study of Riemann is the curved version of Euclidean geometry, or Euclidean geometry was the flat version of it, of Riemannian. On the other hand, there's been actually in the 19th century also some studies that over different kinds of geometry, which are not necessarily Euclidean one. So Euclidean geometry can be described by, with the help of its symmetry groups, which in this case it is the orthogonal group. But the idea of Felix Klein was actually to study different kind of geometry where you would allow different kind of symmetry groups. So this is in the modern terms, so we just call a Klein geometry what we said before, a Lie group and a Lie subgroup. And now to complete the square, we would like something here which actually works like Riemannian geometry, meaning that it is the curved version of Klein geometry, or better, Klein geometry would be the flat version of this object. And these objects are precisely the spaces which were introduced by Élie Cartan, that they call them espaces généralisés, and they are really what now in modern term is just this principal bundle and this differential form, satisfying this property. And Riemannian geometry actually are one key example of Cartan geometries. So now I'm going indeed to give a few examples so that you understand better what are now these Cartan geometries. And indeed, I mean, as I mentioned before, let me just repeat it, that you have this Euclidean space that can be seen as a Klein geometry, where the group H is the orthogonal group, and the group G is just this semi-direct product of ON and Rn. Then a Riemannian manifold is the same thing. So a manifold with a Riemannian metric is the same thing of having a Cartan geometry modeled on the Euclidean geometry. This also may look still quite abstract. So I want to tell you like precisely what should be the P and the theta that I introduced before in this case. So as P, you take the bundle of orthonormal frames defined by your Riemannian metric. This is actually a principal bundle for the group ON. And then as differential form theta, you take this sum of two different differential forms. The first one is actually the connection form of the Levi-Civita connection, which therefore takes value in the Lie algebra H of the group ON. The other form instead is what is called the tautological form, which I will review in a couple of slides, so don't worry if you don't know it. But this is a differential form on P with values on Rn, which have quite some different flavor, because this really is more intrinsic to the choice of the orthonormal frames. It is really separate from the connection. And so here, finally, we can understand a bit why this word in the title about decoupling and coupling. So in this case, what I'm doing is that, okay, I'm looking at a Cartan connection, but I'm trying to decouple it into two parts. And I would like to understand better now these two parts separately, and then the coupling of the two parts back again. This also, we'll be back to that in a few slides. Another key example of that we're interested in are actually some works exactly with the same principle, but we allow any kind of H structure instead of a Romanian manifold. So I will also remind what they are in the next slide, but you can guess that, I mean, in this case, Romanian manifold are really ON structure. But if you take any other H, which should be a linear group, so a subgroup of GL, with a compatible connection, so this role here was played by the Levi-Civita connection, then you really get a Cartan geometry, which is modeled precisely on this Klein geometry. And so these are the kind of example that I'm interested in, this geometric structure that I would like to study them with this different point of view, which is the Cartan bundles, which I'm going to introduce later. Let me also say that there are many other examples of Cartan geometries, which are very interesting, that has been studied in the year. It's just that for the moment, they are not yet relevant for my project, but they are really the example that drive this field actually going, because usually this kind of example of H structure, they are important, but they have already their own theory, the theory of G structures. When people work in Cartan geometry, usually they have in mind example like affine manifold, like projective manifold, and conformal manifold, for example. So these also are very important Cartan geometries modeled on other kind of Klein geometries, which I wanted to mention just for sake of completeness, but they are not really relevant for this talk. So now, as I mentioned, let's focus on this H structure. Let me just remind you what they are and what can we do with them. First of all, just a disclaimer, I should say G structure, because this is the name that they are most familiar for everybody. I am forced to use the letter H out of consistency from the previous thing in Cartan connection. So we are in one situation where either you destroy one convention or you destroy another one. So I hope that, I mean, it's not a big deal for you to just read G like it is, read H like it is here, and think of G like in the title. So what are they? So abstractly, you can define it in this way. You just consider the frame bundle of a manifold. This, remind you, it is a principal bundle over M, which has a structure group, the group GLN. And then a H structure corresponds to reductions of the structure group of this frame bundle. So in particular, principal H subbundle, where H can be any linear group, any group, subgroup of GLN. And this is a very rich theory because you can study many geometric structures as example of H structures. So the first example, we already saw it before. For example, if you take H equal to N, then you get Riemannian structures. You can consider, for example, the symplectic group. This one will you will get almost symplectic structures, so to form which are non-degenerate, not necessarily closed. You can consider GLN and C, which give you almost complex structure, and many other examples. So there are quite some important concepts here. But the way that I want to look at G structure is on a different point of view, which involves this tautological form that I mentioned already before. I'm going to tell you precisely what is that. So the tautological form is defined at the level of the frame. So if you have M, so in your frame bundle, you can define a differential form on the frame which takes values in Rn. And it is defined using this formula here, which may seem that it fell from the sky, but it is actually it's called tautological because it's the only meaningful formula that you can come up with if you want something which takes values in Rn. And so to make sense of it, you should interpret P. P is an element of frame. You should see it as a linear isomorphism between the tangent bundle of M and a copy of Rn. So you define this formula, you define this form, and now what you can do with that? Well, first of all, you can see that this form is quite nice because it satisfies some important properties. For example, the form is pointwise surjective, exactly like Cartan connections. It is also GLN equivariant, so equivariant with respect to this structure group, exactly like Cartan connections. And then if you look at its kernel, you see that the kernel is equal to the kernel of d pi, so is equal to the vertical bundle, not at all like Cartan connection. Because I remind you that in Cartan connection, you had that the form theta was pointwise an isomorphism, so it had no kernel. whereas here the kernel is quite big. It is the entire vertical bundle. Or equivalent, you can also express this property in terms of the fundamental vector field, saying that if applying theta to the fundamental vector field, you always get 0. While in the other case of Cartan connection, you would get back your V. So again, quite a property where it is quite another, you are quite at the other extreme of the spectrum. So this is the tautological form for the frame bundle. Of course, if you have any H structure P, then this inherits the same kind of form, just restricted to P. And of course, it will be H equivariant instead of GLN equivariant. That's obvious. But the nice thing that we like of this tautological form is the following proposition. So it is known that if you take a principal bundle with some differential form with values in Rn, which satisfies this property, 1, 2, and 3, that I mentioned above, then basically you are working with an H structure, meaning that actually there is a modulo an injective immersion, then P really sits inside the frame, and the form pullbacks, in the tautological form, pullbacks precisely to the form theta bar that you have here. So what we have here is basically what we can call abstract H structure, which is in practice the same thing of an H structure, but you can get rid of the frame bundle and have some more conceptual definition, just as a principal bundle together with a form satisfies some properties. And now, well, this is for abstract H structures. Cartan geometries were also defined in terms of principal bundle together with a differential form satisfying some properties. And we saw that some of those properties were the same, and other were of the same flavor, but quite on some opposite side. So what we want to understand is what lies in the middle. Can we get something to describe this thing as part of a more general object? And this more general object is precisely the Cartan bundle. So I'll give you the definition and then comment a bit on it. So what is a Cartan bundle? It is a principal bundle, H bundle, together with a differential form theta on P, which takes values in V, where V, we need to ask that it is a representation of H. Then it satisfies some properties, as usual. Pointwise surjective, I'm not going to comment on that again. H equivariance, same thing, where actually here is important then that V is a representation, so that this makes sense. Then we can look at the kernel of theta, and what do we ask? We ask that it sit inside the vertical bundle. So remember that in one case this was 0, in the other was the entire vertical bundle. Here we ask that it's something in between. And then there are a couple of other properties which are a bit more difficult to understand at this stage, but hopefully will be clearer in the parallel talk when I will explain better the relation with the groupoids. So you have to ask that the kernel is involutive. This actually was trivially true in both cases, because if it is 0, then of course it is involutive, and if it is the vertical bundle, that's also always involutive. But here we have to ask it, because it's not does not follow. And the other property is also, it refers to this to theta applied to the fundamental vector field. So if we take it in a point, basically it should not depend from the point chosen, which again, it was invisible in the G structure case, because this was always 0. And for the Cartan connection, this was always equal to V. So again, it was a different kind of request. Anyway, if we have this notion, then there is also, of course, a dimensional constraint that comes naturally. So the dimension of V actually should sit in between the dimension of M and that of P. And then the two extreme examples are precisely the one that I mentioned before. So we can see that Cartan geometry are precisely the Cartan bundle with these two properties, where the kernel is 0, and V is actually this data G that we have asked for the Cartan connection. So it should be a Lie algebra, which actually contains the algebra H at this condition that I mentioned before. And so it means that the kernel of theta is minimal here, and V has dimension which is maximal, because G has the same dimension of P. The other opposite example is abstract H structure. In that case, these are precisely the principal bundle, the Cartan bundles, where the kernel here is maximal, is the entire vertical bundle, and V is a copy of Rn, so it has dimension equal to n, so that is minimal. Now, this will be the starting point to actually say a lot of the several things about Cartan bundle, which I will discuss in the parallel session. In these last few minutes, I want just to give a few hints about how these things are related to Lie groupoid, because this relation with Lie groupoid will help us to develop actually some theorems, some results on Cartan bundles. And to do that, so since there are many people here that I don't know, I will just quickly review what Lie groupoid is, even if probably it's familiar to many of you. So as the name says, it is something which generalizes the Lie group. and it is therefore, it consists of two manifolds, M and G. You want a multiplication on G, which should be only partially defined, unlike a group. So technically to do that, you need these two maps, S and T, which should be surjective submersion, so that then you can consider this fiber product and define the multiplication on that one. Then you ask that the multiplication is associative, you ask that it admits units, and unlike a Lie group here, there will be many units. Actually, any element of M will be a unit. And you also want to emit inverses. So you should think of element in G as arrows that goes between points in M. And this metaphor with arrows is not only a metaphor, because really an equivalent way of talking about groupoid is saying that they consist of a small category where all the arrows are invertible. And then everything is smooth, of course, because we're talking about Lie groupoid. And another natural property about Lie groupoid, which one want to define, is that of transitivity. So we just say that it is transitive, any 2 points in M are joined by an arrow in G. Now, I could give you a lot of examples of Lie groupoid, of course. I don't have the time, there's not really the place. I already mentioned Lie groups, which are the case where M equal a point. I want to give you this other example, which is fundamental for us, which is the gauge groupoid. So this is a groupoid that you associate to any principal bundle. And it is defined in this way. You just take two copies of P, you take the Cartesian product, HX with a diagonal action on, both on this, and when you quotient, then you can really see that the principal bundle structure induces a Lie groupoid structure on it. This Lie groupoid, moreover, it is transitive. And then I said I will not give you many examples, but if I wanted to give you actually other examples of transitive groupoid, I wouldn't have many to choose, because all of them are the gauge groupoid. So there is this very important and well-known proposition saying that any transitive groupoid is the gauge groupoid of some principal bundle. And the principal bundle actually arises precisely as the source fiber of S of G, and the H, the structure group, is the isotropy of G. So the isotropy is the group of arrows which start and ends at the same point. So now the question is, how does our story look like from the point of view of Lie groupoids? Because what we did here is establish a correspondence. So not we did, we reviewed here, was this correspondence between transitive groupoids and principal bundle. So something that we have here. And now we said that we have discussed before several kinds of structure on principal bundles, like Cartan connection, G structures, and Cartan bundles. On Lie groupoid also one can have several kinds of structures. So the first step actually is to look to study connection on Lie groupoid. So standard Herman connection on G, seeing G as a fiber manifold over M with the source or the target, which are multiplicative. Whereby multiplicative, I mean that they are compatible with the groupoid multiplication in a suitable way. And now, if you have that one, you see that on the other side of principal, you have principal bundle endowed precisely with Cartan connection, which are really the object we looked at the beginning. And there is a one-to-one correspondence between these two notions. This was also in sort of way known, especially from the infinitesimal point of view. So what we did was push something for this comparison even forward, because you can study Lie groupoid which have a more general object than a connection, than a multiplicative connection. So these Lie groupoids are called Pfaffian groupoids. They are just groupoids endowed with some kind of distribution, which were introduced by Maria Amelia Salazar a few years ago. And they were born as the object which encode the nice property of the jet bundle of a Lie pseudogroup. So they were studied to study symmetries of PDEs mainly. And these actually are quite important objects that already also have been used. I also use them in my PhD thesis to study other kind of geometric structures. And they are also useful and relevant here for Cartan bundles, because we will see that Cartan bundles, so that definition that looks a bit abstract that we had before, really comes from here. So that is how we arrived to the definition, then we saw that it was really the good one to choose. So Cartan bundles correspond to this kind of Lie groupoids with this more general kind of distribution, which I will go discuss in the second part. So indeed, in the second part of the session, I will establish better this dictionary between Cartan and Pfaffian reals, saying what they are. And then what can we do with them? Well, for example, we can discuss what I mentioned before, this problem of coupling and decoupling connection, having some intermediate example. And to do that, I will introduce this notion of reductive Cartan bundle. And then, since you start with Lie groupoid and you have a rich theory of Lie groupoid, you can try to move what you know on Lie groupoid to Cartan bundle. Try to make sense of Morita morphism and Morita equivalence, for example. You can talk about prolongations and tower of Cartan bundle in a similar way that you would do for PDEs and for jets of Lie pseudogroups. You can use Lie algebroid, in this case the T algebroid, to talk about coefficient of Cartan bank. And this kind of result and the discussion I would like to do in the parallel session. I think the time is up. So thank you.
Thank you very much for a wonderful talk. So let's thank Francesco with emoji claps. Thank you.
Stop share.